Let's dive right into this explainer and demystify the incredible science behind veterinary diagnostic imaging. Today, we're taking a truly fascinating journey. We are going to follow an X-ray beam from its absolutely violent creation at the atomic level, all the way to how it literally saves the lives of our furry companions.
We're starting off with the ultimate, universal problem every pet owner faces when their companion is sick. Your dog or cat can't exactly point to where it hurts, right? They can't tell you they swallowed a rubber toy or that their joints are aching. Veterinarians are essentially detectives working with silent witnesses. So how do they actually look inside and find the answers? Well, think of an X-ray as the ultimate diagnostic translator for our dogs, cats, and birds. It takes all those invisible internal structures of the body and translates them into a clear visual map that a skilled veterinarian can read and interpret. It's like turning the lights on in a dark room. Here's our roadmap for the journey of the beam today. Section 1, the magic of X-rays. Section 2, inside the X-ray machine. Section 3, making the perfect picture. Section 4, reading the radiograph. And finally, Section 5, enhancing the view.
All right, let's jump straight into Section 1, the magic of X-rays, where we'll look at the fundamental properties of the beams themselves.
So, at their absolute core, X-rays are invisible beams of electromagnetic energy, and they travel in straight lines at mind-boggling speeds. Their real superpower? Penetrating solid objects. But here's the catch. How well they penetrate depends entirely on the atomic number, density, and thickness of whatever they happen to hit. Once they pass through, they act just like light on photographic film, ionizing silver halides to create a lasting image. But we really have to respect this power. Because they can ionize atoms within living cells, they carry real biological risks. And that is exactly why you always see vets wearing those heavy lead-lined aprons. Moving right along to Section 2, inside the X-ray machine. Let's shrink all the way down to the atomic level to see how these machines actually generate the beam.
Picture an atom, kind of like a tiny solar system. You've got the nucleus acting as the sun in the center, and with electrons orbiting around it just like planets. Now this visual perfectly sets the stage for a high-speed collision. You see, X-rays are basically born from kinetic energy conversion. When a super-fast stream of electrons is suddenly slammed into the atoms of a target material, they decelerate fast. They lose their kinetic energy, and that lost energy is emitted outward as X-ray photons.
It's a literal journey inside the vacuum tube of the machine. Step 1, we heat up the negative electrode, that's the cathode, until its tungsten filament literally boils off a cloud of electrons. Step 2, a massive jolt of high voltage shoots those electrons straight across the vacuum. Step 3, they absolutely smash into the tungsten anode target. And Step 4, that sudden, violent deceleration releases our X-ray photon.
Get this though, this high-speed atomic collision is surprisingly inefficient. Literally over 99% of the energy from those smashing electrons is converted into pure heat. Less than 1% actually becomes X-rays. This requires some wild, specialized engineering just to stop the whole machine from melting down. Vets use rotating anodes to spread the heat out, and the tungsten target itself is embedded in a thick copper block surrounded by an oil-filled casing, all just to handle that massive heat byproduct.
Because of all this, vets have to choose their equipment really carefully. A portable unit is great because it's highly maneuverable. You can just plug it right into a standard wall outlet to check out a small dog. But it has low output, which means you need a longer exposure time. If you've got a nervous, wiggly pup who won't sit perfectly still, you're going to get a blurry image. Fixed hospital machines, on the other hand, have massive built-in power. They can snap a picture in a tiny fraction of a second, completely freezing a squirming pet in time to eliminate any movement blur.
Okay, Section 3, making the perfect picture. Let's talk about radiographic quality and how we turn that raw, invisible radiation into a highly readable image.
Think of an ideal diagnostic radiograph, kind of like editing a photo on your phone. It's a really calculated balance of three main things. First, detail, which is the crisp, true sharpness of the image. Next is density, or the literal darkness of the film, which is controlled by tweaking the machine's milliamperage and time. And finally, contrast, that visual pop between the blacks, grays, and whites, which you manipulate using the kilovoltage. But of course, there's a villain in our quest for the perfect picture, and it's called the Compton effect. When an X-ray photon encounters a free outer shell electron inside the patient's body, it can actually bounce off in a totally new direction.
This scattered radiation doesn't carry any useful information. Instead, it hits the film and causes this hazy, washed-out fog, completely ruining your beautiful contrast. Even worse, it acts as a major radiation hazard for the clinic staff in the room. To fix this, machines use collimators. These are physical devices that narrow and restrict the beam so it only hits the exact spot we need, minimizing all that dangerous scatter.
Let's dive into Section 4, Reading the Radiograph. It's time to learn the interpretation rules and see how a vet actually decodes these shadows.
When it comes down to decoding an X-ray, density is literally everything. Remember, you're essentially looking at a shadow graph based entirely on atomic weight. Heavy stuff like bone absorbs the X-rays, blocking them from the film so it pops as bright white. We call that radiodense. Conversely, really light stuff like gas or air lets almost all the beam pass straight through, so it shows up totally black or radiolucent. Soft tissues, fat, and fluids, they sit right in the middle, giving us all those varying shades of gray.
So, applying those density rules to the thorax, the chest cavity, vets look for really distinct deviations from normal anatomy. For instance, an enlarged heart, known as cardiomegaly, shows up as this much larger, rounded silhouette that makes abnormal contact with the sternum. They can also easily spot a floating heart shadow surrounded by stark black air, which is a massive red flag for a collapsed lung or pneumothorax. Or if that crisp line separating the chest from the belly just completely vanishes, and they suddenly see pieces of the GI tract up near the lungs, well, they know for sure they're dealing with a diaphragmatic hernia.
Moving down to the abdomen, the detective work just keeps going. An abnormal, massively distended collection of black gas right at the front of the abdomen can reveal a totally life-threatening gastric torsion, often showing a weirdly compartmentalized stomach. If a dog comes in having urinary issues, vets look for small, irregular white radio-opaque densities right in the middle of the bladder outline. Those point directly to cystic calculi, basically bladder stones. And if they see a dense gray mass physically pushing the bladder forward out of its normal spot, that's a classic sign of prostate enlargement.
And when we're checking out the limbs and joints to figure out why a pet is in pain, a vet is hyper-focused on the bright white structural integrity of the skeleton. They're scanning for diminished bone density, which signals osteoporosis, or stark black lines cutting cleanly right through the white bone. Those indicate painful fractures, literally a complete disruption of the bone's continuity. For common, really debilitating developmental issues in dogs, they are searching for disorganized, thickened new bone formation and a flattening of the femoral head. That's the tragic, telltale hallmark of hip dysplasia.
Finally, Section 5, Enhancing the View. Let's look at contrast radiography and see how vets manage to illuminate the totally invisible soft tissues of the body.
Because here's the tricky part. Muscle, organs, fluid, they all have an average density of around 7.4, meaning they all kind of just blend together into a gray blur on a standard X-ray. To actually see the inside of a stomach or clearly outline a kidney, vets deploy contrast agents. They use super heavy, high atomic weight positive agents like barium or iodine to literally paint internal structures bright white. Or on the flip side, they use negative gaseous agents like room air or oxygen to inflate a structure and turn it pitch black, creating artificial contrast where there naturally wasn't any.
Barium works absolute wonders for the digestive tract because it's totally insoluble. The animal just drinks it down and it paints the entire stomach stark white, instantly revealing any hidden blockages. But obviously, you can't put barium into the bloodstream. For that, vets use highly water-soluble, low-toxicity iodine for a procedure called an IVP. The iodine gets injected into a vein, excreted by the kidneys, and boom, it instantly illuminates them on the screen. And for something as incredibly delicate as the spinal cord, specialized iodine agents like metrazamide are very carefully injected to outline the nerves and pinpoint devastating slip discs.
We really have traveled all the way from the violent atomic creation of a high-speed electron cloud right down to the life-saving diagnosis of a floating heart shadow. It's a pretty miraculous process when you think about it. So I'll leave you with this thought to ponder. The next time your furry best friend goes in for a checkup, what invisible secrets are hiding just beneath the surface, waiting for those atomic shadows to reveal them? Thanks so much for joining me on this explainer, and remember to keep asking questions about the world around you.